Welcome to this explainer. Today, we're taking something that is notoriously complex, the Internet Key Exchange Protocol, or IKE, and breaking it down. We're going to transform all that highly technical documentation you've probably stared at into a really simple step-by-step process. So if you've ever wanted to look under the hood and see how secure VPNs are actually built from the ground up, you are in exactly the right place.
Okay, let's quickly check out our roadmap. We'll be covering the fundamental need for IKE, diving into Phase 1's secure foundation, comparing main and aggressive modes, looking at the Phase 2 data tunnel, exploring the massive evolution that is IKE v2, and wrapping up with why all of this absolutely matters today.
All right, kicking things off with Part 1, the need for IKE.
So, we all know that sending data across the open internet is incredibly vulnerable if you don't have a dedicated control plane. Well, IKE acts as exactly that control plane in IPsec. It sets up a secure channel to authenticate peers, negotiate cryptographic policies, and distribute those all-important session keys. The crucial takeaway here is that IKE actually separates the tunnel setup from the data encryption itself. It's the mechanism we use to agree on the ground rules way before any of your actual user data is ever transmitted.
I absolutely love this analogy. Think of IKE as building a highly secure, soundproof room before you start passing highly classified briefcases of data back and forth. Before IPsec can do the heavy lifting of encrypting those briefcases, IKE has to do the meticulous, behind-the-scenes work of verifying identities and sharing secrets to physically construct that soundproof room. Because, without the room, your briefcases are just sitting out there in the open for anyone to see.
Moving right along to Part 2, Phase 1, our secure foundation. So, how exactly do we build that soundproof room? Well, it breaks down into 3 distinct steps. First, the two parties negotiate. They're basically proposing acceptable encryption and authentication rules to each other. Second, they execute a Diffie-Hellman exchange to mathematically generate a shared secret key. And third, they verify each other's identities. It's a beautifully logical, sequential handshake.
Now, to put that second step into perspective, think about configuring a Diffie-Hellman group in a command line interface. A tiny line of code, like setting a DH group, literally allows 2 network devices to mathematically establish a shared key over a completely unsecured channel. And they do this without ever actually transmitting the key itself across the wire. Honestly, it feels a bit like magic, but hey, it's just brilliant math. Then we hit the third step, making sure the party on the other side is actually who they claim to be. Phase 1 relies on authentication methods to get this done. If you look at standard firewall configurations, you'll often see them set to use pre-shared keys. This takes the whole abstract concept of identity verification and turns it into an explicit, tangible device configuration. Sure, you can use digital certificates too, but pre-shared keys are incredibly common in the wild.
Next up, Part 3, main and aggressive modes. When we're building our secure room, we actually have a choice to make about how we do it. Main mode is your gold standard for complete identity protection. It uses a total of 6 messages to securely hide the identities of the peers. Aggressive mode, on the other hand, cuts that right down to just 3 messages. It's way faster, obviously, but you are sacrificing privacy because those identities end up being exchanged in clear text. So it really just comes down to what your specific network environment prioritizes. The cool thing as network engineers is that we can explicitly command our infrastructure to prioritize that security. By setting the mode to main during your IKE policy configuration, you are strictly enforcing that 6-message exchange. This guarantees that your device identities remain completely hidden from anyone who might be trying to snoop on the traffic.
Which brings us to a really critical question. Now that we have this secure, authenticated channel successfully built in Phase 1, how do we actually secure the specific user data traffic that's going to flow through it? We've got our soundproof room, but now we need to figure out exactly what kind of locks we're putting on the briefcases inside.
And that brings us to Part 4, Phase 2, the data tunnel.
Phase 2 is exactly where we define our IPsec security associations, or SAs. These are the specific locks for those briefcases we just talked about. Now, this phase operates exclusively in what's called quick mode, which is a rapid exchange of just 3 messages. Safely inside our pre-established secure room from Phase 1, the peers quickly select a security protocol, usually encapsulating security payload or ESP, maybe authentication header AH, and they agree on the final data encryption and hashing algorithms.
To see that Phase 2 lock being applied in the real world, think about setting an encryption algorithm to something like AES 128 CBC. You are configuring a very specific cryptographic transformation. Strong algorithms like the Advanced Encryption Standard, or AES, are what will dynamically lock and unlock your actual user data, your emails, your database queries, file transfers, as it securely traverses the internet.
Let's jump into Part 5, the IKE AV2 evolution.
Because technology never stands still, right? Well, IKE EV1 required strict adherence to Phase 1 and Phase 2, which takes a minimum of 9 messages just to start encrypting data. IKE EV2 completely overhauls the whole process. It totally does away with those traditional phases. Instead, it combines the initial security negotiations and the authentication into just 2 primary exchanges, IKE SA init and IKE auth. So now it takes a minimum of only 4 messages to establish that exact same secure tunnel.
The advantages here are just massive. Fewer packet exchanges mean you're using less bandwidth and getting much faster connection times. On top of that, it adds native support for EAP, the Extensible Authentication Protocol, and it has significantly better built-in mechanisms for checking if a tunnel is actually still alive. And because it's so lightweight, if you need to spin up additional tunnels on the fly, it just fires off a rapid 2-message create child SA exchange to instantly get things moving. It's a real game changer.
Finally, Part 6, why this matters today.
Understanding all of this step-by-step negotiation isn't just some academic exercise. As the Palo Alto Network's documentation perfectly puts it, Internet Key Exchange is the cornerstone of establishing virtual private networks using IPsec. Whether you're at a local coffee shop securely accessing a corporate database, or you're managing a massive branch office routing daily operations back to headquarters, IKE, operating silently in the background over UDP port 500, is the unseen protocol that makes all of that trust possible.
So as our remote workforces continue to expand and our traditional network perimeters dissolve entirely into the cloud, I'll leave you with this. How will cryptographic key management protocols continue to evolve to outpace tomorrow's threats? It's something to think about. I hope this explainer has given you a rock-solid step-by-step understanding of the IKE process to build upon. Thanks for tuning in, and keep questioning how your networks are built.